Our final talk in the morning session will be given by Roland Heck. Those of you that flew here on an airplane may know that there is an ozone abatement catalyst used in the air purification system in those airplanes. Many of you, if you're like me, may not have known that the catalyst that's there is an Engelhard catalyst and is used for air purification, reduction of the ozone. And Ron is going to speak to us this morning about the deactivation processes that occur in that system and how that catalyst can be reactivated.
Well, with that nice introduction from Jerry, now I only have a 5-minute talk ahead of me, so he stole the show. Anyway, I'd like to finish this morning's session by discussing a very interesting industrial application of catalysis. In particular, first slide, ozone abatement catalysts, and we'll discuss the effect of the contaminants in the actual intake air for the jet aircraft. And let me begin by now acknowledging co-authors Bob Ferrato and Sho Lee. I think you're going to have to turn those manually. Jerry? You got to do it manually, it's not... The basic reaction is very simple. It's a decomposition of ozone to oxygen, but I'd like to give a little background on how this occurs. In the late 70s, early 80s, with the fuel and energy crisis, the aircraft were flying at much higher altitudes, 30, 40,000 feet. And they also were taking routes over the polar to fly to Japan. And when you go through those areas, you bring ozone into the aircraft. The way the aircraft is pressurized, you take air off the compressor stage of the jet engine, it goes into the aircraft. And as you're flying through these areas where there's ozone, it goes into the aircraft itself. And it's a lot of physiological problems associated with ozone in the aircraft. So the idea is to put a device on board in the aircraft to remove the ozone. They tried things like carbon beds in the very beginning, but they were very ineffective because they had to be removed and they weighed hundreds of pounds. So we came up with a catalytic device, and the device has actually been in use since 1983 in the aircraft itself. Let's try this again. No, stop. The basic reaction is on a honeycomb surface. This schematically shows just the bulk gas flow. And the type of reaction mechanism you're seeing is bulk phase mass transfer, reaction kinetics, and actual pore diffusion mechanism. So you can have all of them going on the catalyst. Next slide, please. Gotta wake them up. Thank you. This is a cutaway of the actual ozone abater. You can see that it's a honeycomb catalyst. Flow in this direction itself. Next slide, please. Just go ahead. This shows it being placed in the underbody of a 747. In the 747 aircraft, for instance, there's 3 ducting situations. 2 of them are always used, and the third is redundancy in case anything happens to one of the duct systems. And this is the actual air is passed through the converter and then through some other filtering devices into the aircraft, and that gives you your pressurized air in the aircraft itself. Next slide, please. This shows you the coating of the honeycomb. The coatings on the sidewalls of the channels are anywhere from 10 to 20 microns in thickness. In the actual corners themselves, you can get up to 100 to 150 microns. And what I'm going to show you in some later slides is actual analysis of contaminants in that region, and also analysis of contaminants along the channel itself. Next slide. Okay. Through some studies in actual reaction kinetics, we've been able to find out that the actual ozone reaction is controlled by diffusion of the ozone to the catalytic surface. So it's a bulk phase mass transfer controlled reaction, which means that you want the highest geometric surface area possible. So we operate with 300, 400 cells per square inch honeycombs. Next slide. Since 1983, we've been trying to develop a replacement pattern for the aircraft. So you can imagine these things are installed in planes, and the question is, what is their effectiveness? How long is the life of the catalyst? What's happening while the catalyst is on stream? This is a plot of percent conversion. There we go. 0 to 100% versus flight hours going out to 25,000. And these are two lines that represent 50% of the points lying above that line, 85% lying above that line. So here's the target itself. So you can see you're running about 15,000 flight hours before you're falling below the target. And of course the question is a lot of scattering data. What's happening to the actual abaters themselves? Remember, this is the air that's being ingested into the aircraft itself. So originally you think, well, it's nice, clean, pristine air. No problems. Next slide. This shows a simple kinetic study where we looked at the conversion of a fresh catalyst, and you can see that typical mass transfer conversion response, we're at this temperature, we basically have no function decrease in temperature, so it's bulk phase mass transfer controlled. A return catalyst after 20,000 flight hours, you can see what's happening. You've lost enough activity, so now the catalyst is exhibiting a kinetic response. Combination core diffusion and kinetic activity. So the catalyst has deactivated sufficiently enough so it's in kinetic control right now. So what's happening? What's happening to the catalyst? Next slide, please. We did some analysis on the catalyst, and the first series I'm going to show you is along the channel length. So these are bulk samples that are taken every inch along the catalyst length and analyzed by X-ray fluorescence. And I also must apologize because a few of the slides after this are going to be a little bit difficult to read the way they came out. Anyway, if you look at 10,000 flight hours, and again this is long the length, you see a fairly flat profile for phosphorus. As you go up to 25,000 hours, you see a threefold increase in the phosphorus concentration, but still a pretty flat response along the axis of the honeycomb surface itself. Now, I'm pointing it out because that's a little different than you would see in automotive catalysts. In automotive catalysts, you see this very, very sharp response and then falling off. So we have a different situation. And it can be attributed to the fact that we're running at much lower temperatures. This is typically 200 degrees centigrade, 250 degrees centigrade. Next slide, please. This is where the slides get a little tougher, but I'll try to walk through them and get to the point of it. Anyway, the 10,000 hours and the 25,000 hours for silicon, it's a very small difference. There's your 10,000 hours here, and your 20,000 hours here. It's out of focus now. Still out of focus. You see it's out of focus here. Okay, so for silicon, you can see that there's a fairly flat profile again. but notice there's a substantially higher concentration of the silicon versus the phosphorus. Okay, next slide, please. This is the sulfur analysis going from the inlet to the exit. Very little difference between 10,000 and 25,000 hours. And notice that this sulfur profile is fairly flat. So on the return catalyst, we're seeing one, phosphorus contamination. The phosphorus contamination increases with time on stream, looking at sampling at 10,000 and 25,000 hours. However, if you look at the sulfur and the silicon, it's a fairly flat response. In other words, the sulfur on the surface and the silicon on the surface equilibrates very fast. That's better. Whatever you did, it's good. Just leave it here. Did I get extra 5 minutes, Jerry? Okay. So, this is, again, to remind you, this is along the axial length of the honeycomb. Now I want to go ahead and take that corner channel I was looking at before that has about 100 micron thickness of wash coat, and we're going to probe that using an electron microprobe. Next slide, please. Okay. This is now is the phosphorus at the corner location. 10,000 hours, very low concentration of phosphorus at corner location. Okay. When we go to 20,000 hours, you can see a very sharp surface concentration of phosphorus. As you go into the wash coat deeper, essentially the same as it was at 10,000 hours. So, for phosphorus, high surface concentration on the wash coat. Flat axial response, but surface concentration on the wash coat. Next slide, please. Okay, this is silicon, and you can see that silicon has also a higher surface response. This would be the 10,000 hours here. Okay, and if going to 25,000 hours, a slight increase. Notice also the high levels of the silicon. By the way, this is identified as silica, basic silica dust, and the phosphorus is basically as a phosphate, and also the sulfur is as a sulfate. Next slide. This is the sulfur profile at the wash coat corner. See, very flat response before we went on that analysis. And here you can see an increase in the sulfur level, but again, uniform throughout the wash coat. So, surface concentration for phosphorus, very sharp. Still surface concentration for silicon, not as sharp. Sulfur is uniform throughout the wash coat. Okay? At the 25,000 hours. So what is this doing? Next slide, please. This is the pore size distribution of H catalyst, looking at 10,000, 25,000 hours. I'll go through the 10,000 hours, which is right here. Down in there. And if you look at the 25,000, you can see a decrease in this porosity region and an increase in the smaller pores in the nasal pore region. So what's happening is the contaminants are plugging the pores. Okay? So you have pore plugging occurring during the aging of the catalyst. So we have three contaminants. We have the sulfur, we have the phosphorus, and the silicon laying down the catalyst and losing porosity, basically. Next slide, please. This gives you an idea of the CO-chem resorption profile. The catalyst itself is a palladium-based catalyst, and some earlier work that we've done and published shows that palladium is the preferred catalyst for this reaction. Platinum is passivated, and a lot of base metals are passivated by ozone. Initially, they have superactivity, but after 10 hours, they have no activity. Platinum maybe lasts for 100 hours. The ozone itself, but does not passivate palladium. So, whoops. If you look at the the concentration the CO chemisorption profile here. This would be at 25,000 hours. It's declined to 0.4 square meters per gram. If you look at the 10,000, it's much higher. But there's a decline of about 50% in the CO chemisorption. Next slide, please. Summarizing some of the physical measurements we did, looking at the porosity. The initial porosity is about 0.25. The BET surface area is about 100. The mean pore radius is close to 50. After 10,000 hours, you can see the porosity has substantially decreased, about 1/3 of its original. The BET surface area has decreased also by 1/3. The mean pore radius is about the same. However, there's a substantial reduction in porosity or shifting of it. 25,000 hours, you can see that there's further reduction of porosity, further reduction in BET surface area, and a lowering of the mean pore radius. And this corresponds to that shifting of the pore size distribution to the smaller pores, or actually in the mesopore region. Okay, next slide, please. Now, as all good scientists, we have a postulation of what's going on, and this cartoon shows a little bit. We've been able to take these catalysts and actually do a rejuvenation using chemical washing techniques that we practice with almost all our environmental catalysts. And you can regenerate these catalysts. And in the regeneration, what happens is you remove the phosphorus. Both the silicon and the sulfur remain essentially on the catalyst, but the phosphorus is essentially quantitatively removed. So what we think is happening is the sulfur is tied up with the wash coating in some kind of serial aluminum complex, not affecting the palladium activity. The silica itself is really a dust-like material that doesn't preferentially block the catalytic sites, although it's present there in a very large amount. What we think the phosphorus is doing, though, is coming over here. And it's actually masking the catalyst, covering the palladium sites and actually covering up the pores. So if you can imagine, we term masking, it's like taking a piece of Scotch tape and laying it over a piece of catalyst. When you regenerate it, you remove it. So we can actually chemically clean the catalyst and remove the phosphorus and return it to its initial activity. So we feel that what's happening here again is another example, as we've seen in a lot of industrial catalysts, that what's happening is materials are actually masking the catalytic compounds. It's a reversible poisoning that can be removed by chemical washing techniques, which selectively takes off the masking compounds and restores activity. And some of you are familiar with some of the work in the literature shows that this also happens in catalysts for VOC applications and SCR NOx and NSCR NOx, etc. So it's another common phenomena. In this case, it was experienced in ozone abatement. The sulfur itself, by the way, is present in ground level contamination. When the aircraft is sitting ready for takeoff, the jet fuel itself, sulfur contamination we think is occurring. Both the silicon and the phosphorus come from lubricants. They're in the underbody of the aircraft. They're flame retardant materials, they're hydraulic fluids, and somehow they leak into the system and they get into the air ducting themselves. So the sources are pretty well identified as far as where they're coming from. Next slide, please. Okay, in conclusion, the catalytic ozone abaters are capable of performing successfully for up to 25,000 flight hours, and Jerry mentioned in the beginning. They've been on aircraft since 1983. They're on all the wide-body jets. They're on a lot of the private aircrafts now also. We found out through this study over a number of years that the major contaminants are phosphorus, sulfur, and silicon. And we've identified where those contaminants come from. We've also identified that the catalyst can be rejuvenated using chemical washing techniques. We postulated that masking of the catalyst, okay, is actually the way, the mechanism by which the active sites are covered, the pores are clogged, and that is reducing the catalyst performance and useful life. Okay, thank you. Questions?
Yes. Cal?
Yes, Cal.
So that you maintain about a 90% conversion.
No, it stays constant. What happens is that in the aircraft, in the ducting itself, the air comes off a certain compressor stage, let's say the third stage, and that's constant. So you have the isentropic temperature rise of that compressor. When a jet takes off, the temperature's higher. When it goes to cruise, it's lower. And so the temperature's modulated throughout the life based on the operation of the aircraft. So we don't change it. We don't change that function.
I just wondered, towards the end, then, are you actually getting lower conversion?
We have a replacement policy that we worked out with the airlines based on this study. I mean, that was the only, because there's no way of carrying on board a cheap ozone analyzer except you know, as a body, you know, and so we developed through bringing catalysts back, testing them in a test rig, a replacement policy with all the airlines.
Just another comment, and that is, it seems that through a strategy of pore design of the pore structure in the catalyst, you might be able to get extend the life of the catalyst.
Yeah. In fact, we have a paper in Catalysis Review that was published a year and a half ago that describes our second generation catalyst, which solves this problem. I mean, it does a better job on it.
And it is, of course, it is a change in pore structure then.
Yeah, and some other things, but that's part of it, yeah. Yes.
Satish Kamakar from BOC Group.
Yes.
You mentioned target of 60% conversion. What is typical inlet concentration of ozone?
Well, the regulation is based on the cabin itself. 0.1 ppm is the regulation. The concentration into the aircraft changes because what happens is the ozone concentration in the troposphere is not a constant. It changes. And it can range anywhere, I remember, up to 3 to 5 ppm ozone. So if you fly through the high level concentrations, then you're coming in with 5. If you fly through a different level, it's 3. So it changes, it varies. But the FAA requirement is, I think it's 0.1 ppm on an 8-hour exposure. So that's what has to be met. And believe it or not, all parts of the aircraft decompose a certain amount of ozone. The seats, the vinyl, everything does. So there's a factor for every piece of equipment in the ozone, and they add them all up to meet this regulation.
I was wondering why the target is set based on percent conversion rather than actual level.
Because experience has shown that that's sufficient at that. And that's a sufficient time for replacement, yeah.
Other questions? Yes.
If palladium is well dispersed in the catalyst, can you say something about deactivation by oxide formation? If it's small particles at operating temperatures of 150 degrees in air?
You mean, the palladium itself is in the oxide form all the time because it's 21% oxygen, so it's always has palladium oxide. It's not reduced. Does that answer your question?
Yes.
Other questions? I have one, I guess, Ron. You said that the chemical washing removes the phosphorus, but not the silicon or the sulfur. I wondered, first of all, how much additional life you get on the rejuvenated catalyst. I guess that's the main question, is what effect does that washing have on the activity for the second generation?
We're still working on a commercial process to implement that. What we did here was to try to see if the washing techniques we've used in other applications would regenerate the catalyst. Indeed, they did. And then when you went back and analyzed it, you found out that you were selectively removing the phosphorus. But I don't think that we're implementing that as a commercial practice right now.
So right now, they're not rejuvenated ozone abatement catalysts that go back into the aircraft. Those are new catalysts when they're replaced.
They're working on it, Jerry, but they're not there yet.
All right.
Almost.
Okay.
Okay? I don't want to steal everybody's thunder on that. So.
All right. Yes.
Yes.
Heinz Roland Heck signal. In explaining the scenario of how the catalyst deactivates, you showed us quite a bit of data relating to the way in which the phosphorus was deposited with regard to its profile on the surface layers, and you talked about changes in porosity and changes in surface area and things like that. At the end, you told us that by washing it, you can remove the phosphorus, but you didn't really tell us anything about what happens to the surface area, the porosity. Do you recover all of the porosity that you previously had? What level of recovery do you get? And I'm particularly curious because in the thick web of the wash coat, that's where most of your catalytic or substrate material is, and that's where you're going to be measuring your surface area. It looks like your phosphorus didn't penetrate more than, say, 25% into that region. Yet you were losing something on the order of 75–80% of your surface area because you went from 100 basically down to 18 or something like that. So you weren't penetrating all of the surfaces, yet you were losing what seemed to be a disproportionately high fraction of the total surface area. So I'm wondering if you could comment on that.
All of them or just...
Yeah, sure. We have time.
Well, let me start with the one at the end. If you look at masking, okay, you can have a very small deposit, but if you think of it as the Scotch tape thing, you can lose all your BET surface area. So that's an easy one, okay? And it doesn't mean that it goes into the pores, it means it just lays on the surface, okay? And a lot of the washing techniques remove that covering, okay? And been very, very successful in VOC abatement. We have a paper where we got like 10 years operating experience with catalyst to wash. Okay, so it's very successful there. In like applications, I don't remember the numbers here, you can easily recover 50% of the BET surface area, and I think in some cases even 90% of the BET surface area. Okay, so it's a very, very successful technique. Very successful. Is that all of them?
That pretty much covers it.
Okay. But the key is that if the mechanism is this non-selective poisoning, which we've dubbed masking, and other people have dubbed it too, it can be removed very easily. And even when it's in the pores, it can be removed very easily too. So it's opened up a whole new arena for industrial catalysis, as you probably know.
Yes.
You,
Step to the mic, please.
I'll yell.
Okay.
Do you know if the poisoning occurs as a slow and steady, or is it episodic, a big belch of whatever phosphorus?
There have been some big belches in airplanes, yes. Okay? I'm serious. What happens is the hydraulic fluid, when you lift the wheels up, that hydraulic fluid is a flame retardant, which is a phosphorus-based compound. And they have had seal leaks, and that seal leak runs under the underbody aircraft and gets sucked into the ducting and goes into and they had people that go on oxygen before. So yes, it can be catastrophic. 99% of the time, though, it's a slow, small seal leak that's occurring for the phosphorus. Okay? The sulfur and the silicon seem to equilibrate quite fast, as opposed to the phosphorus, as those slides show. The silicon we feel is also a grease lubricant, but apparently is much more available in the ducting atmosphere. Okay, you use a lot of silicone greases for various types of seals and everything and ducting. So that's coming in very easily. Okay? Does that answer it?